Everyone, we doing good? How was last class? It's okay? Now today will not be so bad. We have one little corollary to finish up and prove, and then we'll go to examples, all right? We will go to the computer and we set up examples and we'll solve it, and then we will play with that. So what I plan to do, okay, so I would like to go through the highlight of what we did last class, put up the main results, and talk a little bit about it, so get all the results clear in our head, all right, before we move further, because there was quite a bit from last time. So let's do this. Some kind of a review. Okay, so let me write. So we have the max problem. Let's set this up. Maximize z c dot x subject to so that's the original problem, and then you form the dual, which is a minimization problem. So let's just set this up. Min equals b dot y subject to so the original problem, and it's okay, that's stated in the standard theorem. So let's state these results. Okay, like the main thing, I'm not going to write it in a very wordy way. So theorem one, kind of at the base. So if I find two feasible solutions, x0 and y0, they are feasible solutions. So it's clear that x1 is for the max problem, and x0 is for the max problem, y0 is for the main problem. Two feasible solutions. If that is the case, and then we have the following. Then the objective function for the max problem is bounded by the objective function for the main problem. Actually, they bound each other. One gives upper bound, one gives a lower bound, right? Okay. So that's the first theorem, which we went through the proof. The proof is like half page on my notes. So it's a pretty nice short proof. Would you be able to reproduce it? I should put it as homework, like close the book and repeat this proof. Will we be able to do that? Okay, so make sure you you know how to do that. All right, so based on the follow from the corollary theorem 1 in the proof, we have the following. So if you have just two feasible solutions, and you know this guy is bigger than that, how much is it bigger than that? Well, that's determined by actually the slack. So the difference between these two objective functions equals to y naught dot u plus x naught dot. Now, I used v in the notation last time, which maybe I should not have, because v is here. So let's call this w, okay? So where u would be what? U is the slack for the first, so it's b minus ax, and w is the slack for the second one, which is a transpose y0 minus c. So those are the two slacks, okay? And that exactly, the inner product of these two adding up give you the difference between these two objectives, right? So that was proved together in the proof of theorem 1, if you remember. And based on that, we have a short, like, logical argument to reach this corollary 3. So if, in addition, this inequality sign now becomes equal, in the setting of theorem 1, if we find two feasible solutions where the min and max exactly take the same value right there, and then a very simple argument shows that these two will be the optimal, actually. So the z max will equal just that number and is the v min. Do we remember the proof? It was 3 lines, right? Just arguing, and that's it. It has to be, okay? All right, and corollary 4 also follows from theorem 1, very simple proof. This proof here is the homework. You practice on that, okay? So here says that if in the case that one of the problem has unbounded objective function, then the other one is not feasible. It's a symmetric relation. So let me write out just one way. So if z in the max problem is unbounded above, you can show that min is not feasible. Okay? And the other way around also holds. If the v for the min problem is unbounded below, then the max problem is not feasible. Okay? That happens. That's a homework problem. Okay? And then we have the big theorem, theorem 5. That's the main one, the duality theorem. That's the main thing. Took more than half of the class to prove it, right? So it's really... So that theorem says, now, take either one of these, either one if it has a bounded optimal solution, and so does the other, and those two optimal values equal each other. Okay, so let me write it. So if either max or min has a bounded optimal solution, and so does the other, then they will both have optimal solution, and then they are the same. So z max will equal v min. Okay? So that took us quite some time to prove, right? So, okay. And I don't know, do we remember some of the details in that proof? We proved it only for the case where the b on the right-hand side is bigger than 0. We started from the max and showed the result for the min, right? We consider the case where the right-hand side b is non-negative, which makes this proof a bit simpler. If you want to consider the right-hand side also containing negative sign, that is assigned as an optional homework problem. If you want to show off to me your proving skill, go ahead and do that one. Okay, it's very similar. It just gets a bit longer because you have to argue a few more things. Okay, and also in the proof, we notice that when you, okay, so this is a constructive proof. The proof goes through the simplex algorithm and looking at the last row of the tableau and conclude a lot of things right from there. So that last row of the tableau is particularly important in this setting right now. So let me highlight. The last row in the tableau. Okay, what does it contain? Well, it contains the coefficient in front of the variables for the objective function. Is that right? Something times x1, something times x2, add up, equal z, where z reaches the optimal value. Is that right? So these coefficients, so in particular in the proof, it relies heavily on the fact that the coefficients there for the slack variable, okay, actually gives you the optimal point for the dual. Okay, so you could actually just get information from there and find the solution for the dual problem without actually solving the dual problem. Okay, so that's that. Okay, so let me block this. So this is what we had last time. Do we all remember? Any questions on that? We okay? All right. So I'll give you one more corollary with a very short proof, and then we're done with the theoretical part. So that's number 6. Okay, so let me state it first, then we'll look at it. Okay, so let's look at it. So what does it say? It says if both max and min, the two problems, have feasible solutions, meaning it's feasible, meaning I can find some x so that the constraints are satisfied, right? Or I can find some y and this constraint is satisfied. If both of them are feasible, then I can conclude that the objective function, they will all have optimal values. You can solve it. And they equal each other. The max equals to the min. Is it clear? Do we see the difference between this corollary and theorem 5, or any of the things we stated before? So how is this different from theorem 5, for example? The conclusion is the same, right? We conclude that Z max equals V min, and they both have optimal solution. It's the assumption is different, isn't it? So what is here is assuming. Here just assume that you have feasible solution to the constraint for both, right? And then in theorem 5, the assumption is different. Theorem 5 says, not for both, I just take one. For example, I can just look at max, and I see that not only I have feasible solutions, but I managed to find the max of Z, which is bounded. So do you see there are two different constraints? Okay? So this corollary 6 says, with that assumption, I can reach the same conclusion. Okay, so make sure that you pay attention, that's different. All right, let's do a little proof. So in the proof, there's no computation and nothing. It's just logically arguing using the results on the left, those that we proved last time. Okay, so theorem 1 is very important, actually. It allows us to prove many things. So let's see, what is the assumption here? We assume both max and min have feasible solutions. Okay, let's look at how theorem 1 can help me. If I find a feasible solution, x naught for the max, and a feasible solution y naught for the min, what do I know? I know that the objective function for the max is less than the objective function for the mean. Is that right? So let's say I find a feasible solution for the mean, so I get this number. And that says that for any x naught that's a feasible solution, this guy is bounded by that, which means z has an upper bound. Do we agree? And you can argue symmetrically, well, and so v would have a lower bound. It cannot be less than this value for a x naught that's feasible. Do we see? So let me put that argument down, okay? So what I mean, so we know that both have feasible solutions, and then I use theorem 1. I can conclude that both the objective functions z and v are now bounded. And in fact, I can be specific. Z is bounded above, because you see, z is this guy. Z is less than something, which we know is finite, okay, bounded above. And v is bounded below. So if z is bounded above, and you are trying to find the maximum value, then of course it exists and is bounded. Is that right? So this easily implies, now this implies, let me write, the max value of z and the v, the mean value of v, they are now both bounded. Is that okay? Now I changed it, didn't I? I argued, and then I showed that this assumption we start with now leads to the conclusion that, take z for example, the z max is bounded. So now I know the max problem has a bounded optimal solution. Is that right? So does the mean. Actually, I conclude both. And now I see I can use theorem 5. Theorem 5 says, if the max problem has a bounded solution, then so does the mean, and then I have that. You simply apply it. Okay? So let me just write. Then by the duality theorem, 5, we conclude z max equals v. And that's it. Is that okay? Do we see? It's a very short argument. Is that right? Just use whatever you have already established. Okay. Okay, so let's do a little summary and just summarize 3 different cases that can occur in these, the problem and its dual and the solution of it. Okay. So let me write. So the book says 4, but actually 2 of them are the same. So 3 categories of solutions. So the first one is the nice one, where you can apply the duality theorem. So both have feasible solution. And then you would conclude z max equals v min. They all exist and they're bounded. And then the second one is from corollary 4, which to be proved by you. You will prove it. Which says if one is unbounded and the other is feasible. So if one objective function, one of these is unbounded, and then this will imply the other is not feasible. Is that okay? So if the max problem doesn't have an upper bound for the z could go to infinity, then you know the mean problem won't even have any feasible solution. Okay. So the other way around will be if the mean problem, the objective function is unbounded below, it can go to negative infinity, and then the max problem would not even have any feasible solution. Okay. So that's in this case. And then the third one is, well, that we're really unfortunate that both problems have no feasible solution. So both are not feasible. Then there's no solution at all. Okay. So is that clear? All these results, all these concepts in our head? Mm-hmm. So now I will go through a couple of examples. So in the other class, I managed to do 3, and the last one was a bit rushed. So don't waste too much time. Let's see. I will apply the duality theorem. I will set up a problem and set up its dual, and we'll go to LP Assistant, and we'll solve it, and we will verify the duality theorem, and we will verify all these observations that should happen, okay, just to get it very clear. So I will take one example from the book. I mean, it's just number. You can put in any number, but okay, in the book, we'll copy this one from the book. So I want to maximize this one. Subject to, let's put up 2x1, negative x3, x2, x4, 30. Less than 24. Okay. So that's the original problem, and then we know we can form the dual. So the dual will have three variables, y1, y2, y3. This is a very standard max problem. You can just form it following the definition. I have a minimization problem, 20y1, 30y2, 24y3. Okay, so let's let that be. So let me call this z and call this v. Okay, so we can refer to them. Subject to y1. So are we professionals of forming the dual if it's given in this standard way? We're okay? You assign a y1, y2, y3, and then you just multiply and you add them up column-wise, right? Okay, so the objective function will be these cross the y, and then I do this coefficient cross y, and it should be restricted by the coefficient there. Okay, so I'll just write this out without much fussing over, assuming that we're okay. If it's not clear, you ask, and I can explain more. Okay. Okay, so as a practice, you can write it out by yourself and see if you get the same thing. All right. Right. Okay, so we will go to, we'll solve this by simplex method and using the LP assistant because we need to see the tableau. We don't want to use Excel. It doesn't give us information. Yeah, did I do something wrong?
Do you mean right next to max, should that be a 15? Or should the low be 5?
-5. And that's -1. I copied it wrong. Is that right? Yeah. It's this number comes in here and this, yeah. You're right. Thank you. Okay, so think about you have a problem like this and you want to go to LP Assistant and solve it. How would you do it? So you know the LP Assistant takes a minimization problem in a canonical form. Is that right? So let's say I want to solve this one. So what I will do, I will change this into min. So I need to change the sign of all these coefficients. I will be minimizing -z. And then since this has inequality sign, I need to put slack variables. I'll need to add a slack x5, x6, x7 to make this equal sign, right? And then you see after adding those 3 slacks, these 3 slacks can be used as basic variables. And I have it in canonical form. I can already solve it. Is it clear? Can we all see it and look at it and see that's what we have to do? I will not write out the canonical form before I punch it in LP Assistant. I'll just punch it in, okay? And now look at this, the dual. You know, in the end, you want the right-hand side to be positive. So before adding the slack variable, probably I would multiply the first and the fourth by -1 to change the inequality sign. And after I've done that, I will add the slack. I will have to add 4 slack variables, y4 here with a plus sign, y5 with a negative sign, y6 with a negative sign, and y7 with a positive sign in the front. Then I have equal. I have it in standard form. Once you've done that and you see the first slack and the last slack can be used as basic variable, not these 2 middle ones because they have -1 in front, right? So what do? You have to add 2 artificial variables. And you have to go through stage 1, drive W down to 0, and do stage 2. Is that clear in our head what we have to do? Okay, so we will go to LP Assistant and just show off our skills. See, I can do it. It's a lot of fun. So, okay, so let me try to punch in these numbers. So for the original problem, I have 1, 2, 3 equations, 3 slack, 4, so I need 7. So I need to add a couple more variables. 1, 2, 3. I need to go all the way to 7. Is that right? And I need 1 more constraint. Well, you can launch it up and you can try it and see if you are faster than me and get the result. So let's punch in the number. 2, -1, 1. If I do anything wrong, yell at me and let me know right away. 30, 24. So I punch in the right-hand side. 0, 1, -2, -1, and 1. That's the second equation. And the third one, -3, 6, 3, 4, 1. And then I identify the basic variables. So for the first equation, it's x5, and the second is x6, and the third one is x7. Is that right? Yeah, question?
On x4, the first row, you miss 3.
2. Oh, I missed the 3. There. 1. Yeah, okay. Okay, anything else? Did I get the numbers right? Okay, then the objective function, I need to multiply by negative sign. So I have 5, -18, -6, and 1. Is that correct? Am I ready to pivot? Let's do. pivot. Let me make this a little bit longer. So I need not that many steps. Okay, so let's see. I see a negative, big negative, negative 18. Let's check the ratio. 4, 30. So I click on 6. Is that clear, my choice? Click on that. And then I have another negative number, negative 4. And then I see the ratio is 52 and 10. The smaller one is 10, and I click on that. Is that okay? And then I see I have all positive, non-negative numbers here. So I'm done. Will we be able to write out the conclusion from this tableau? What does it mean? What solutions do we have for this one? So let me write out solutions on the right-hand side here. So this means the Z max, actually we have to take a step here. This number, the negative of this number gives me the minimum of negative Z. Is that right? Therefore, the max Z is just that number. So actually, you put 2 negative signs in your head to just get that number. Okay? Z max is just 112. Obtained at which solution? So I have 4 x's. So I know x1 is 10, x2 is 0, 3 and 4 are, 2 is 9, and the 3 4s are 0. So at 10, 9, 0, 0. Is that right? Okay. So let's try to solve the dual. Let's put it side by side, and then we can compare. We can find connections in the tableau. So let me put this over here. Actually, that one needs more space, so let me shrink this a bit. Not so much. Yeah, more important than that. Okay. So for the dual, look at the dual here. I have 1, 2, 3, 4 constraints. So let's see. I can add a constraint and add a constraint. I have 4 constraints, and then I know that I need to add slack variables, 4 of them. So I will have 4 plus, I have 7 variables. So 4, 5, 6, 7. Okay? So let's punch in the numbers. So for the first inequality, I already said I'm going to multiply by -1 everywhere. So I will have -2, 0, and 3, right? Y4 will be my slack. And the right-hand side, 5. I want to make it positive. Is that clear what I do? If you see mistakes, let me know. And the second one, I have 0, 1, 6. And the slack variable will be minus, so it's a -1 here, y5, okay? And the right-hand side is 18. Okay, and the third one will be -1, -2, +3, and the slack variable will be y6, which will carry a negative sign. And the right-hand side is 6. Okay? And the last one, I will multiply by -1 to change the inequality. So I can add a good slack. Okay? So I have -3, 1, -4, and I will have 1 here, right? And the right-hand side will be 1. Is that clear what I did? Okay, let's put in the objective function. It's minimizing, so I'll punch the number in 20, 30, and 24. Okay, let's identify basic variables. For this one, I can use x4. For this one, I can use x7. But then I don't have more. Is that right? So for these two, I will have to declare an artificial variable. I add one artificial here, and I add an artificial variable here. Is it clear why I do all these? Now I set up the tableau, right? Now I can go and pivot. So stage 1, I need to drive W down. I need to drive it to 0, meaning I need to make this guy 0 by pivoting. So I have a negative sign here. Let's check the ratio. 2, 3, 1. So I'll click on 3. That's 1.6. It's a small ratio. I click on that. And then I see that I have a -5. And this is not 0 yet. I need to keep pivoting. So I have two positive numbers, 1 ratio 2. So this one has a smaller ratio. I click on that. Is that okay? Are you all with me? And then I see I still have some bunch of negative 1 because this is not 0 yet. So let's look at negative 9. And it has only one positive coefficient in that column. That's the one I will click. Okay, now good news. Now I made it 0, which means I finished stage 1. Now I go to stage 2. Now look at these. So now I will neglect all these yellow parts, pretend they're not there. Okay, now I have original problem in canonical form. You see that? So now I look at these coefficients, and there is a negative 1. And in this column, there's only one positive 1. So I click on that. Okay? And now there are no negative coefficients. So I managed to find the optimal value for z. So let me lift it slightly higher so I can see it here. Yeah. Okay. So what have we, what did we get in the end? What will be the solution? Can we write it out from this computation? So the V min will be the negative of this. Is that right? So V min will be the negative of this 1, 1, 2. Okay? Where is it obtained? For the y value. So I only care about y1, y2, y3, because the slacks I don't care. So what will be y1? Okay, they're called x here. y1 will be 2, y2 is 0, y3 is 3. Is it clear where I get this? Okay, at 2, 0, 3. Okay. So let's make observations and make connections. So the first problem, we found a maximal solution. By the duality theorem, we know already the dual will have a minimal value, bounded, which will be the same as the max value for the first one. We observe that in this example. Is that right? Okay, then there is something more. In the proof of the duality theorem, so the duality theorem proof is based on this max problem that we have here. So let me make this just a slightly bigger so it's not that unimportant. Okay, so the proof of duality theorem is based on this max problem. And we show that in the proof that the coefficients, this last row here, the coefficient in front of the slack variables here will be x5, x6, x7. These three numbers are important. The proof says these three numbers shall be the optimal point in the dual problem. Do we see that? 2, 0, 3. Where is it coming here in the dual problem? Well, it's exactly this optimal point where it attains the minimum. Is that right? Okay, so that's verified also. And now something else which we didn't verify. Let's make this observation. So you will be curious, okay, will that observation also be valid on the, is there so much light? Okay, let it be. Can we see the screen? Is it okay? Okay, let me don't fuss over. So is this observation also somehow valid to go from here back there? Is the optimal point for the original problem hidden in the last row here where you have the objective function? The optimal point is 10, 9, 0, 0. Do we see it? Over here. 10, 9, 0, 0. The coefficient in front of the slack variables. Is that right? So that is very important. That's why this last row is of importance. Okay, so and then this leads to my next comment. As you see that for these two problems, to solve the max problem is much easier. Do you agree? Even with LP assistant. Imagine you have to do this by hand. You would not want to go through this big tableau, wouldn't you? You would prefer to do that one. Imagine if this were the original problem you want to solve, and you see, so much trouble. And then you write out its dual, and you see, the dual is quick to solve. So you can instead solve the dual problem. And in the dual problem, in the last tableau, you extract the solution for the original problem. You will know that the optimal value will be that. It will be attained at 2, 0, 3 there for this problem that you don't have to solve. You can just get information from there. Solve the one that's easier to do because they have the same thing. Yeah, question? Usually, if the constraint is less than equal, you add a slack variable that can be a basic variable. And if it's bigger than, that's no good because you have a negative sign. And then you have to do artificial variables. Is that clear? So these conditions will be easier to handle. Okay. Is that okay? So that's the example of verifying duality theorem and also some more observations and connections. Okay. Okay. So okay, I have half an hour. So okay, let's see if I can go through 2 more examples. Okay, so let me take another example. We'll not go through the LP assistant for this one. Okay, so this will be more like a problem that I could possibly put in the exam because I cannot let you use LP assistant. So it has to be something based on applying the theorems. Okay, so I would verify that x not equals 0, 5, 2/3, 8, 1/3, and 1/3. Let it be a column vector, okay? Is an optimal point to the following problem. Minimizing. These are not very nice numbers, but okay. Subject to okay, just numbers. So basically, I have an A matrix times X on the left, and I have a vector on the right-hand side. I write out the 3 equations, okay? I want you to verify that gives you the optimal, provided I give you also this one to check, 3.5. Let me give a label to it, and why not equals that, 2, 1.5 transpose, the column vector, is an optimal point of the dual. So you have a dual problem, and I'll ask you to verify that this will be the optimal one for the dual. So it's important that I give you this x naught and y naught. Okay, otherwise this will be very hard to prove without using softwares. Okay, otherwise this is too much. Okay, so answer. So how about we do this with a vector notation, matrix vector notation would be easier. May I form a matrix of these coefficients? Will be okay? So let now A be the coefficient matrix. Okay, you know how to form it. You just copy the coefficients. Let me copy. And -1, 5, -2, 1, 1, -4, 3, 5. That's the coefficient matrix, right? And I form the right-hand side vector 2, 12, and 4. Okay? And then I form the coefficient vector, these ones. So I have 7, 11, -3, -1. Okay? And with this, it becomes a bit easier to write out the things, right? So step 1, form the dual. Okay. So the dual for this problem will be maximizing instead of min, right? So not a C dot. Okay, so would it be okay if I write the original problem? So I rewrite the original problem. The min now can be written as minimizing, what would that be? Minimizing C dot x subject to A x bigger than B, x bigger than 0. Then I can just write in one line, all right? Rewrite it, just make it easier. And then I can write the dual. Dual will be maximizing B dot y subject to A transpose y less than C y bigger than 0. Is that right? So I can form the dual just by definition. Okay. And now step 2, I need to verify. Before I can claim this is an optimal point, I need to first verify if it's feasible or not. If it's not feasible, there's nothing to talk about. So verify that x naught is feasible. Okay, what do I mean? Well, I need to show that A x naught shall be bigger than B. Is that right? Now A is a matrix. X naught is this vector. Here, you just have to perform this product, matrix times a vector. Okay, it's some work, but not impossible, right? So you can carry out this computation matrix by vector, and you will get this number on the right-hand side, 2, 12, and 4. And then I see that is exactly B. So the constraints hold. So that's feasible, right? And then you compute the z value. So the z value at x dot, which is c dot x naught, what would that be? So you take the c and take the x naught, and you do the dot product. Okay, multiply 4 numbers and add them up, and you will find you get 37. Okay, so I shall allow calculators for the exam, so you don't have to struggle too much with these numbers. It's not meant to be done by hand. Okay, then I will do a similar thing for the y naught. I will verify that y is feasible. So A transpose y naught, this that's given here, shall be feasible is less than C. So they're all positive, so for sure that part is okay. So if you do this computation, A transpose y naught, it's a matrix times a vector, isn't it? Again, I will get the following numbers: 6.5, 11, -3, and -1. That's what I will get. And then compare that to the C, 7, 11, -3, -1. So these three matches, and this one is smaller, right? So it's less than C. So it's feasible. And then I need to compute the V. Did we call that V? Okay. Okay, so now I compute this value of y naught dot. The objective function there would be B. Okay? So you know the B, you know the y naught, and you compute that dot product. It's just add up three numbers, and you find that's 37. What can you conclude by this computation? That's the observation. They attain the same value. Is that right? What can I use? Which of those theorems that we have covered can be used to conclude something? Or corollary, actually. If I find a feasible solution, x naught and y naught, and this product equal each other, the objective function takes the same value, then that value is the optimal value for both problems. Is that right? By quoting that, you verify this. Okay, so conclude by corollary 3 and 37 is the max and the mean for these two problems, respectively. So you reach that. And therefore, these two are the optimal points, this one and that one, is where it reaches the optimal value. Is that clear? It's just applying corollary 3 here. Okay? All right, so that is that. That's some problem I could ask you without you having to do too much computation. Okay, so I would end with one more example. It's more like an observation. We really didn't really prove anything in that direction, but you could easily imagine they can be proved. So an example where the constraints carries equal sign. So we know from earlier discussion that if you have a constraint with equal sign and you write out its dual, you will get a variable with unrestricted sign. Is that right? And how does this theorem play out? Or how do all these observations relate to each other? Do they still hold or what? So I want to do that. So this is an example with the equal sign constraints. Okay. Okay. All right. So let me put that. It's okay. So minimizing. Z equal 16 x1 plus 32 x2 plus 12 x3 subject to x1 plus wait a second, that was not the one I wanted to do. No, that was the other one. That was a mixed one. So let's write it again. So smaller numbers. Subject to, and actually this is a max. So it's easier to follow the max of that. Subject to x1, x2, 5x3, x4. Oh, I'm so sorry, my brain is not with me. Let me try again. It's just numbers. Okay, so let's write numbers. 3x1 plus 5 x2 plus 9x3. Okay, let's put two equations for the constraint, not too big, because 12x2 plus 15 equal 90. Negative x1 plus 2x2, 3x3 equal 12. Okay, so two equal sign in the constraint. And if you want to write out its dual, are we okay to write out the dual? So the dual will contain two variables, y1 and y2, one for each constraint. And they will both be unrestricted, right? Because they come from equal sign constraint. Okay? So let me form the dual. Minimizing the following, 90 y1 plus 12 y2 subject to 4 y1 minus y2 bigger than 3, 12 y1 plus 2 y2 bigger than 5, 15 y1 plus 3 y2 bigger than 9, but they're unrestricted. They can be positive or negative. There's no restriction on that. Okay, so let's think to solve the first one with LP assistant, thinking in that direction. You see, this is in standard form already, but not in canonical form. Not in, okay, if I change this into minimization, I'm in standard form. But this is not in canonical form, so I need to add two artificial variables. And then I can start the process. Is that right? And for the dual problem, I have two unrestricted variables. What do I have to do? Well, I have to break this up. I have to write y1 equals y, let's call it w then, w1 minus w2, and y2 is, oh, w is not a good number because we use the w. Okay, y2, because I need to label my unknowns. I need to do that. Is that right? And then I plug it in, and then I need to add 3 slack variables. And then you know they are the wrong sign. And I need to add 3 artificial variables. There's tons of work there, but you can do it. Okay? So we want to see some connections here. So let's try. Let me close this. Let's open a new problem. Okay. So for the original problem, this shall be reasonably small, so I'm not going to give it too big a window. So we see we have 2 constraints, 3 variables. So let's put that in. Let me get my number here with me. So I have, is that 4, 12? Yeah. 4, 12, 15. And the right-hand side is 90. And then the second one is -1, 2. Sorry. I typed it wrong. -1, 2, and 3. And the right-hand side is 12, right? And the objective function, I need to change into minimization, so I have -3, -5, and -9. Yeah. Did I punch all the number in correctly? And then I see I have no basic variable, so I add an artificial, and I add an artificial. Are we all okay clicking this? Now I'm ready to pivot. Okay, so I need to drive this number down to 0. So I have a -18. Let's check the ratio. 4, 6. So I click on the 4. And then I see I have -9. That's the only positive one. I click on that. Okay, now I drove it down to 0. And once I drove this down to 0, I will neglect this yellow part. They don't matter anymore. Then I only look at the original problem, which is in canonical form, and the objective function has actually a non-negative coefficients, right? So actually, I'm done. I reached the optimality. Okay, so with that, we write out. So what is our optimality here? So the maximum value will equal to the negative of this guy. Is that right? So 56 obtained at, what are the x values that it's obtained? See, x1, I have it, and x3, I have it. So 10 over 3, and x2, 0, is a 40 what over 9? What is it? 46 over 9. Okay. And that is nice and easy, right? So do you think we shall dare to do the dual problem? Mentally, in our head. I will not write down all the steps. So from the discussion we had, we know I need to break it into 4 variables. Y1 bar to Y4 bar, and then need to add 3 slack variables. So I need 7 variables, right? So let's give all these variables. So all the way to 7. Okay. And how many? 1, 2, 3 constraint. I need to add one more problem. Add a constraint. Okay. So now you know this guy is breaking into Y1 bar minus Y2 bar. So actually I have 4, negative 4, right? And then at this I will have negative 1 and positive 1. So I need to put more coefficients there. So let's do that. So what would I have? 4, negative 4, negative 1, and negative 1 and 1. And then I add a slack variable, but with the wrong sign. Okay? And the right-hand side will be 3. Okay, let me punch all the right-hand side. 5 and 9. Okay, and then the second equation would be 12, negative 12. To indicate I add these artificials, and 2, negative 2. And the slack variable will be there with negative 1. Is that clear? And then here I will have, is that 15? Negative 15. I break this into 2 variables, and 3, negative 3. And the slack variable I add will be negative 1. Is okay? And now the objective function. The objective function, I also need to break this y1 into y1 bar minus y2 bar. So I have 90, negative 90, and 12, negative 12. Okay, so let me put that. 90, negative 90, 12, negative 12. Okay. That is in standard form. And then I see I don't have any basic variables. So I need to add 3 artificial variables. Is that clear? Add 1 here, add 1 here, add 1 here. Do you all get this? Are you trying on your own? Is that what we get?
The second row, x4 will be negative 2.
x4. Oh, okay. Then I have to remove the variables, and then I have to redo it because I need to do this when is correct. I removed the wrong variables. Okay, I will add one more. Add a regular variable, and that shall get a negative 1 here. So this number I messed up, right? Negative 2. Is that correct now? Okay, now I can add artificial. Add an artificial, and artificial, and artificial. It gets quite big. Let me check. They all look good? Okay. Let's pivot. So what do I have to do first? I need to drive this number to 0. Look at negative 31. Check the ratio, 0.6, 0.4, 0.7. That's the one. And I click. It's not 0. I have these two negative numbers. I think this is more negative. It doesn't really matter. So I have 2.2, 4. So I shall click here. Is that right? And then I still have negative. So this is negative. And that's the only positive one. I click here. Now I see I have driven this guy to 0. So I'm good. And then I'm done, because all these are non-negative. Do we see that? Okay, so I finished this computation with the simplex. So let's write out the conclusion. So the conclusion is the minimum shall be the negative of that. Is that right? So the minimum here shall be the negative of that is 56, and we already take a glance over there. Oh, it matches. It has to. And where is it obtained at? That's obtained at where x1 is 2 over 3. Okay, so let's write it out in terms of these y1 bar, y2 bar, y3 bar, y4 bar. That will be 2 over 3, 0, and x3 is 0, x4 is negative 1, 3. So this will be with these y1, y2 bars. Okay? You want to go back to the original one. What is y1? What is y2? Well, y1 is this minus that. Is that right? Let me check. Did I copy the right number? 2 over 3, y3, y1 minus y2. Yeah. x1, x4. There is a wrong sign here. Why am I getting a wrong sign? Okay. Thank you. All right. So this minus that is 2 over 3. I know what the final answer has to be. And this minus that is negative 1/3. Is that right? And now you see it is unrestricted because the optimal solution is obtained at this y2, which is negative. So the two problems give you the same solution. And I would like to make also the further observation. I want to say that the answer here for the dual problem is actually already hidden in the last tableau where we computed the original problem. So you know the optimal value. Oops, that window is covered. Sorry. Let me click on that. So that window goes on the top. So you know the original problem, you find the optimal value is 56. Then you know it's the same for your dual problem, right? And you see the coefficients in front of the, right now is the artificial variable. 2 over 3, negative 1 over 3. It's the solution for the dual problem, right? Okay, so do we find the other way around? Do we see these three numbers in the tableau of the dual problem somewhere? Do we see it? Isn't it right here? Is that right? So the same observation is observed again here. Okay, so I want to say that we actually didn't prove for these more general cases, okay, our proof is based on the maximum, the max problem with the dual as a mean. But you can take that proof and extend it to the other cases, just a bit more work. The same result still holds. Is okay? Yeah. So, yeah. Okay. Any questions? Now, in the textbook, there are a couple more examples with equal sign and inequality sign in the same problem. You should read them. Is that okay? Can I require you to do that? Read that before you do the homework problems, okay? So it will be very useful. So let me put it on the board. So read and try it out, and plus try it out the other examples in the textbook. So get yourself very, very comfortable with this and with very sharp eyesight and spot these connections. Okay? Right. Let me stop here.